Okay, so how is everyone today? Good. Very good. So we've turned in a few written homeworks. Terrific. You have problem section tomorrow. The topic of problem section tomorrow will be, among other things, similar topics to those homeworks. And just generally what was gone over in week one, because what's happening on Monday? No, well, Monday through Saturday. Nothing's happening on Monday. Party's happening on Monday. But at any rate, what's happening next week? The quiz over week one. Okay. Good. So any questions about any of that? Okay, so then my office hours are now set and posted. I'm trying to get the sign up for the oral exam all squared away. But if you just catch me in my office, you can come do it because someone already did. Fermat's theorem. Someone already did it. And it wasn't that bad, I think. I'll let that person speak for themselves. Any questions? Yes?
How many times are you meeting you in office, like for the exam?
3 separate times.
So is that each time you're going to select what theorem you're going to do, or you're going to select?
You can do whichever one. You can say, I'm here to do whichever one. Yes?
Can we do them all at once?
You can, but you have to let me have a break. You can't do the same one twice in a day. So it's pass-fail. If you don't get it, you can't do it again that day. You've got to do it some other day. But I guess it's fine as long as no one is desperately needing to talk to me if you wanted to do this one and then the next one and then the next one. That'd be fine. Yes?
In fundamental theorem of calculus, you invoke mean value theorem, right? So can you do that without having first proven mean value theorem?
Well, I'll accept if you do it. I will accept it if you do them in the wrong order. Sure. Today's what, the 31st? Other questions? Okay, so last time we had finally started talking about getting just a little bit into topics about linear algebra. Just as a reminder of things that you already know from linear algebra. The standard basis Okay, so would someone remind me for a given linear space, what is a basis? A set of vectors that spans the space. And generally speaking, we're almost always talking about Rn for some Rn, like R2 and R3 and R2370 and things like that. If you have a 9-dimensional space, how many vectors do you need to span such a space? 9, right? Okay, good. So the standard basis for R2, the way that we will denote it, the standard basis is E1 and E2. So I'm aware that it may have been the case in other classes that you called these I and J, but that's not what we're going to call them. So specifically, E1 is 1, 0, and E2 is 0, 1. Okay, probably no surprise when I say that the standard basis for R3 is denoted E1, E2, and E3. Okay, and then what are the coordinates for E1? Very good. 1, 0, 0. And then for E2, 0, 1, 0. And for E3, exactly what you expect. Okay, generally speaking, I'd like for you to recall or learn for the first time the definition of the Dirac delta function. It has two subscripts, A and B. Does anyone know the definition? This is new? Okay. So that's a delta. It's equal to 1 when A and R is B, when the two indices are the same, and it's equal to 0 otherwise. This is the discrete delta function. There's another thing that's also called the Dirac delta function. Sorry, I'm not sure who was saying it. I just heard it was over here. Where you're talking about continuous things, and we're distributions, and that's not what we're talking about. So, for example, I could say, what's delta 3,3? It's 1. Whereas delta 3,4 is what? 0. So in Rn, the basis vectors are called E1, the standard basis, E1, E2, all the way up to En. And then if you have the kth one, Ek, then its coordinates are delta K1, delta K2, dot, 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 delta Kn. So why does this work? Why does that work? Why is this a legitimate definition?
So the 1 in the K.
Right, because almost all of these delta K whatevers are going to be 0, right? In fact, exactly one of them is going to be 1, and that's where it says delta KK. All the others are going to be 0. Okay, good. Any question about this? So this definition has the same ambiguity and weakness that the IJ stuff has, and that is that sometimes I means 1, 0, and sometimes it means 1, 0, 0, right? Whereas E1 here means 1, 0, and E1 here means 1, 0, 0. So just be careful when you're looking at it. Any question about the standard basis vectors? Okay, so the last thing we said last time is we were talking about a vector field, and we gave a somewhat trivial one, a constant vector field. So let's have one that's slightly more interesting. How about f of x and y is x and y. So now, previously, the output was some constant. I think it was 1 and 2, or 2 and 1, or I don't know. Now the output is not constant. I could ask, for example, what is f evaluated at 2370? 2370, right? So let's plot a little bit of what this looks like. You can't really plot too much of it because it gets kind of crowded. Okay, so now, where I'm making these dashed lines, everywhere they intersect, we're going to plot the output of the function. So those are integer lines. So what is the output at position 0, 0? 0, right? So I'll just draw a point there. Okay, what is the output at 1, 1? 1, 1, right? So then, so then that means we need to go over 1 and up 1. So the output right here looks like this. So at position 0, 0, that is to say, at position 1, 1, at position 1, 1, we have output, which is the increment 1, 1. So it looks like this, 1, 1. Notice the square parentheses and round parentheses convention. Position 1, 1, increment 1, 1. Okay, let's continue. How about at position, what position is this? 1, 0. So at position 1, 0, what's the output? 1, 0. So that means over 1, up 0. So then it would look like this. I'll draw it just slightly above, otherwise we wouldn't be able to see it. Okay. How about right here? Zero, 1. So its output is 0, 1. So that means left and right we move 0, and then we move up 1. So how does it look? Straight up, right? Except I'm going to draw it just a little bit to the side so we can see it. Okay. How about this one? So this is position -1, +1. So that means from that position we're going to go that way. Okay, so like this. Okay. Fine. So then probably no surprise when I say that this one looks like this. 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 Any question on those so far? So what we've done is at all these positions, we've done it for all the green positions so far. Okay. Let's do it for a few more. How about for this green position? So what position is that? 2, 2. So that means that from position 2, 2, we're going to have to give an increment of 2, 2, which is just like this one, except what? Longer, right? So from position 2, 2, this is increment 2, 2. Okay, how about, what's the position right here? Yeah, so this is position 2, 1, which means we're going to increment by 2, 1, because that's what the function is saying we're doing. So that means over 2 and up 1, right? So then, just eyeballing it, that's about 1, that's about 2, so about right there. Okay, this one right there, that's 1, 2. So then from here, it looks something like this. Okay, from here, something like that. How about this one? What will this one do? 2 to the right. Okay, and then finishing it out, this one would look like this. This one like this. Which other ones can I do? This one like this. This one like this. This one. Beautiful. So I didn't draw any points, any grid points besides the ones that are labeled, but just for concreteness sake, what if I were to put one more point, say, right here, at half-half? then what would it need to do? Half-half, right? Good. Interesting. So, you know, you can use your imagination as to what this might represent. You know, when you look out in the universe with a telescope, it kind of looks like this. Everything is receding from us. Well, if you get far enough away. Okay, everything's flying apart. Any question about this? Okay, another one. So how about f of x and y is, how about y negative x? Okay, this is another really common vector field. So let's plot it. Again, I'm going to go 2 integer positions in each direction. Gesundheit. Okay. So again, I'll do the easy one. I did it. Okay. So at position 0, 0, the increment is 0, 0. Okay, fine. So how about at position 1, 1? What's the increment? 1 negative 1. So that means that move to the right by 1 and move down 1. So that's here, right? Yes?
Does it matter that one and then one to the
Well, let's write it down. So I might have made a mistake. I'm kind of now second guessing myself. So at position 1, 1, are we all in agreement that that's position 1, 1? Okay, the output that we should draw is 1, negative 1. So we're going to move right 1 and down 1. Yeah? Okay, good. I was kind of like worried I was losing it. Right 1, down 1. So like this. Okay, good. So how about this position? What is this position? This is position 1, 0. So that means that we're going to go, the output is going to be 0, negative 1. 0, negative 1. So we're going to go exactly down, like so. Okay, good. That is to say that this is 0, negative 1. Okay. How about this one? So that's position 1, negative 1. 1, negative 1. And what will the output be? Negative 1, negative 1? Very good. Okay. How about this position? This is position 0, negative 1. So what will the output be? Negative 1, 0. So we'll go exactly left. Okay, this is position -1, -1. How will we move? -1, +1. Okay, so the picture's starting to come out, I think. Okay, how about this one? This is position -1, 0. So what is the output then? 0, 1. So that is to say, straight up. Okay, how about this one? This is position -1, +1. 1, 1 is the output. And this is position 0, 1. So what's the output? What is it? 1, 0, right? Okay. So let's do just a couple more for completeness sake. How about, say, this one right here? So that's position 0, 2. So then what do we do? 2, 0, which means 2 to the right. Okay. Now I hope you believe me when I think you could probably tell me what is the increment from this position? 2 down, right? And what's the increment from this position? 2 left. And from this position, 2 up. Okay, so I leave it to you to fill it out some more. But what this is doing is that this is a swirling vector field. It's all of the vectors are pointing in these directions. All the increments are going like this. So this could be something like galaxy rotation or rotation of a weather system that happened recently, or lots of other things, right? But the thing I want you to take away from this is, from both of these examples, is this is what vector fields are like, is that you have a position, and at that position you have a function that defines for you an increment. So at this position, increment like so. At this position, increment like so. At this position, increment like so. Okay, so any question about this kind of idea? Okay, good. This. Okay, so this is the definition of a linear function. So f from Rn to Rm, so notice that the input vector size is potentially different than the output vector size. Okay? In principle, they could be the same, but potentially they're different. This is linear when, how many conditions are there for linearity? 2. Okay, and I hope that you get a very strong echo of what we talked about last time. So, what's one of them? Homogeneity. That is to say that f of ax is what? Right, a multiplied by f of x, and this is for all real a and all vectors x in the reals, in Rn. Homogeneity. So you can factor out scalar multiples, or if you like, scalar multiples commute with application of the function. Okay, 2. What is the other property of linearity? Additivity. Additivity. So now what's the condition? Right. That the sum, you take any two vectors and compute their sum first, and then apply the function second. That's the same as what? Right, doing function application first to both of them, and then adding them together. So do understand that this addition right here is occurring where? This is occurring in Rn, whereas this addition here is occurring where? In Rm. Okay, so a linear function. Let's have an example of a linear function. Do we have one? Well, we'll just make one up. So let's consider the following function. F of x and y is, how about that swirl one? What did we say it was? Was it y negative x? Okay. There's two swirls, right? One of them going the one way and the other going the other way. But they're both obtained by swapping the positions of the coordinates and negating the other, right? And I couldn't remember which one I arbitrarily chose. Okay, so is this linear? Oh, there's a question, yes?
As far as how to tell what function's linear, I was going to ask, is the inverse true? If something is additive and homogeneous, is it linear?
Yes, this is the definition.
So the inverse is also true. So it's
Yeah, these are equivalent. Exactly when both of these are true. So this is a thing,
right.
and this is a thing, and when you have both of these things, it's called linearity. Okay, so how about this function? It's linear? Are you sure? Because like when we were plotting it, it was all swirly. I didn't see straight lines. Right? Linear, doesn't linear kind of remind you of flat a little bit? Well, let's see, right? There's just one way to see if it's linear. Okay? So you must satisfy two requirements, homogeneity and additivity. Okay? So is it homogeneous? So how do we confirm or deny that? Yeah. Let's take a vector. Let's take a scalar a and multiply it by that. So how about ax, ay? Ax, ay. Well, according to the definition, what would we get? Ay and negative ax, right? And then, according to the rules in linear algebra that you already learned, can you factor out a scalar? Sure you can. So this is a multiplied by y negative x. But of course, y negative x is exactly what f does to x and y. Whoops. So it's homogeneous. Is it additive? Well, how do you confirm or deny this?
Add some vectors.
Add some vectors together. So how about f of, say, here's where the position and increment distinction gets a little weird. So I'm going to do it like this. So x1, y1 plus x2, y2. Okay, so now I'm going to add those two vectors together first. I'm going to perform the addition first, which is to say I'm asking about f of x1 plus x2 in the first coordinate and y1 plus y2 in the second coordinate. Well, this is y1 plus y2 and then negative x1 plus x2. Now what?
Definition of addition. We can do that.
We could distribute the subtraction to get y1 plus y2, negative x1 minus x2, and then yes, this is y1 negative x1 plus y2 negative x2. But of course, what is our other name for this? Yeah, that's f of the first vector, and this is f of the other one. Okay. Okay, good. But we must have one where it's not true. So how about, for example, f of x and y is, say, x squared and then y. So is this linear? Yeah, we have to confirm or deny using the definition, right? So what are the two things that are required? Homogeneity and additivity. So let's test homogeneity. So f of ax, ay, according to this definition, is ax all squared, ay, which is a squared x squared, ay, and we can factor out an a to get this. So, is that f of xy? No, it isn't, right? We have too many a's. So this is not homogeneous. It's not homogeneous, and therefore what's the conclusion? Probably where? Yeah, this should be squared. So it's not homogeneous, and as a result, this is not linear. Yes?
Do we reduce the definition of a linear function down to something like if it contains any nonlinear operations and it's not linear? Like if we know that just the x squared operation is not a linear operation.
Okay. What's the definition of a linear operation?
Linear combination. We use that definition. I don't think it's...
Will it be so? I'm about to answer your question. Okay. So this is not homogeneous. We're all in agreement there, right? So not homogeneous, and therefore not linear. So one of your questions that I'll pose tonight is to try and imagine what would it be like. What would it be like to have a function that is just one or just the other, or to have a subspace that's just one or just the other? Can you think of a subspace that is homogeneous but not additive? Or can you think of a subspace that's additive but not homogeneous? Okay, so let that run wild in there for a little bit. Okay, so here's more or less the answer to your question. And this is a theorem that you had to study in linear algebra, and that is that every, so in the first place there's two halves to the theorem. Every m by n matrix A, so the matrix's name is A, defines a linear function on Cartesian copies of n. So the signature, there's sort of two possibilities, and I want to ask which one is which. So is it going to be Rm to Rn? Is the standard way we look at it, or is it going to be the other way around, Rn to Rm? So which one of I'm asking you, which one is the correct one,
The second,
and why?
because you have to multiply a vector in Rn to transform it, right? So
Mhm.
the rows of this guy, or so the columns of this guy has to match the rows of how many elements are in this one.
Very good.
So, yeah.
So when you look at this matrix, since it's m by n, one of these letters represents columns and the other rows. Which one is which? What is this one? Rows. And this is what? Columns. So if we want to perform multiplication of a vector on the right, that is to say, we want it to look like a matrix that looks like this, a rectangular matrix that is m by n, and we want to multiply it by a vector, a column vector on the right. My question to you is what size does this need to be? N by 1, since it's a column vector. So how can you tell from linear algebra that this is a compatible multiplication? Right, these match. That means that this is a compatible multiplication, and as a result, what is the size of the result? M by 1. So this is the kind of output that you get. Output. So is everybody clear that it is this one that is the correct one? Okay, inputs of this kind, outputs of that kind. Okay, so every matrix A generates a linear function in the following way, with the function t of x is what? Ax. By the way, the reason why we're going to insist that all, maybe contrary to your previous experience, the way we're writing functions like this. So we write functions with the outputs stacked vertically, and the input stacked vertically and the output stacked vertically. The reason is because you want linear functions to look like this. If you wanted them to be rows, then you'd have to do some other thing and put it on the other side, and it would look weird. Okay? So every matrix defines a linear function. Okay, that's obvious enough from your experience in linear algebra. The thing that's less obvious that I can't recall if you actually learned it in linear algebra is that the opposite is also true. That is to say, if you have a linear function, if it's a linear function defined in any way that you like, then you can figure out a matrix which represents it. That is to say, every linear function is representable as a matrix. Multiplied by its input. It has no apostrophe. So if we have a linear function t from Rn to Rm, then the matrix of t has columns given by t applied to each basis vector. That is to say, so the way we'll denote the matrix of t is to put t inside of square parentheses. And that matrix is, in the first column, t applied to E1. That's the first column. The second column is t applied to E2. And what's the last one? En. So is it En or is it Em, the last column? N, right? Good. So any question about this? So this more or less answers your question. That could we have addressed this by watching what it does to the standard basis vectors? Well, you could have plugged in the standard basis vectors and come up with a matrix that was given by those columns, and then you could ask yourself, is the function that is generated in that way exactly the same as this function? And the answer would be no. It is not. And so that the answer to the question of whether or not this one is linear would have to be no in that case. Any question about this? So that's a linear algebra result. Okay, definition. So we have this definition of a linear function. A linear function is linear exactly when it's homogeneous and additive. And even better, we can come up with a matrix representation for every linear function, and every function that is a matrix times its input is also linear. Terrific. So here's a slight relaxation of that definition, and this is affine. Okay, so then a function f from Rn to Rm is called affine when this function, the function that takes an input x and produces that function evaluated at x minus that function evaluated at 0. So are we familiar with this? Maps to? So when this is linear, I'll make another remark about what that means. So the maps to symbol can be done in the following way. We could say that f, here's something that you learned in college algebra, so probably no question about what this means. Okay? But what I want you to see is that another way to write this is that f is equal to the anonymous function that, oops, I don't want to give that x a hat. f is equal to the function which takes an input x and produces x squared. So what I'm telling you is that these two things are the same. These are the same thing. Yes?
The initial function x bar maps to x minus f0 or what?
That's a subtraction, and this is, of course, the origin. So what I mean is that the purpose of this is that sometimes you're not really in the mood to give a function a name. So I'm not even bothering to give this function a name. So in some context, the maps to operator is called the anonymous function operator. It's how you make a function that has no name. I'm not interested in its name. I'm just interested in what it does. Okay, so then f, so this by itself is a function, the thing that takes one input x and produces the output x squared. And what this is saying is we're calling f that. F is going to be that thing. Okay, so now, what's the distinction between linear and affine? Exactly this. So remember, if you take a vector space and then map it with a linear function, the result will still be a linear subspace of the range. Okay? So that is to say that when you take a linear function and you look at its graph, its plot, it's going to be flat. It's going to be a flat thing in the target space, in the codomain. Okay, so then furthermore, because of the homogeneity property and the additive property, where does a linear function take the origin? Yeah, if you input the origin, the zero vector, into a linear function, what do you get out? 0 in the other space, right? This origin maps to that origin. So what a linear function does, now I can only really draw, please understand that this applies in all finite dimensions. A linear function is going to end up being flat and through the origin. So flat in the sense that there's no bendiness, it doesn't bend at all, and it's also going to pass through the origin. Okay, whereas an affine function is still going to be flat. Still going to be flat, but it doesn't necessarily have to pass through the origin. Yes?
So every linear function is also affine?
That's right. Yes. Affine is a weaker condition than linear. So this is on the horizontal space, this is the origin right here. That's the origin right here. And where does the function map the origin to? Right there, at that point, right? So now I have a question for you. What if I were to grab this blue point right here, the one on the top, since you can barely see that that's blue, and pull it down to the origin? If I was to just pull it down. Yes, and all the stuff moved rigidly with it. I pulled the whole thing down by the blue point until it was on the origin.
Subtracting the f of 0?
Yeah, that is to say, I'm subtracting f of 0. If we were to move this down, it would be linear. That's what this definition is saying. That's what this one is saying, is that if it's flat, but not necessarily going through the origin, if you just pull it down to where it is going through the origin, then it would be linear. Okay, good. Now, the reason why that's relevant for our class, because it can kind of be easy to lose the forest for the trees, is that when you take some function then the differential point of view in calculus is to say, well, I'm particularly interested in this input here, and I'll call this input x is c. And then the output of the function is right there. And then the differential point of view is that everything is happening locally. So let's be really, really, really local. That is to say, let's get really, really small. And if we were creatures that lived on the red function, but we shrank ourselves to be really, really small, then how would the red function look to us? It would look flat. Okay, now, so that's the tangent space. Is the tangent space linear?
No, it's affine.
It's affine, right? It's affine because it's not passing through this origin, right? It's not passing through this origin. So typically, what you do is that, this one is the x-axis, and this is the y-axis, the input axis and the output axis. So it's not passing through the origin there, but it is passing through the origin here if we were to move the origin there, right? If we were to move it there. And that's what this previous remark is saying, is that, well, yeah, I agree that the origin of coordinates was set over here, but I'm not interested in that. I'm a little creature crawling around right here. I want the origin to be here so that the tangent space is a linear space right here. So typically the tangent coordinates, this is called the x dot space, and this is the y dot space. So these are the tangent coordinates. So it'll be, we don't need to get into that a lot right now, but just know that now this is linear in these coordinates. It's affine in these coordinates. Good. Any question about any of these things? Yes?
So if it's affine, it's not homogeneous, but it's additive? Because after the origin, it can't be homogeneous.
It also can't be additive. It's not going to be either, probably. Can I think of something that's affine? Can I think of something that's...
It can't be either because, well, I mean, unless if it's also linear, it can't be either.
Yeah, something that's strictly affine.
0, 0, it would give you the different.
Yeah. So I don't think there's any functions that are strictly affine, that is to say affine but not linear, that also have homogeneity and additivity. I think if once it's affine, if you have either one of those, you have both. Maybe I'll set an exercise for that. Now you've got me thinking. I'm not sure if it's true. It could be. Okay. Good. So what I'd like to point out, one thing I'd like to point out before we move to the next thing, is that essentially none of what we've talked about has anything to do with geometry. It's all been just sort of abstract. And by geometry, I mean being able to take two vectors, say, and measure the angle between them. Right? Nothing we've talked about at all says anything about angle, how things are situated with regard to each other. And nothing that we've said says anything about the length of a vector. How big is it? Right? Big ones versus little ones. Nothing that we've said. So now we need to talk about the geometry. So this is section 1.4 in the book. We're just going to briefly review some geometry. So the first definition that every school child knows is that if we say let x and y be in Rn, then we have the dot product that everyone knows and loves. What's the definition of the dot product? X transpose y. Every school child knows. So, by the way, so x is a column vector because Rn always means column vectors. It never means row vectors. So that means that this thing, x is n by 1. N by 1, and this is n by 1. So now I have a question here. What does transpose do to a column vector? Right, it you know, at least on paper anyway, it flops it to the side and makes it a row vector, right? So what is the size of X transpose? 1 by n. And then what is the size of Y? N by 1. So of course, at least can we all agree that the output's going to be a scalar? Okay. Another way to write this would be the sum from I is 1 to n of xi yi. This is exactly the thing that you know. There's no difference between what you've already learned about it. Okay. So any question about it? This is fine? Okay, so that's the definition of the dot product. And believe it or not, adding this one definition gives you every bit of the geometry in Rn. It tells you everything about length, it tells you everything about angle, it tells you everything about projections, it tells you everything. So one thing I want to caution you about, or at least since you're math majors, I want to put it in your head so that you can file that away for later, is that historically speaking, it took a long time for mathematicians and physicists to realize what role the dot product was playing and to try and figure out which results actually do depend on the dot product and which ones don't. Because there's plenty of times where you're dealing with Rn, but you're not talking about an Rn that has the dot product. Not every Rn has the dot product. So for example, an example of Rn could be something like we might be wanting to purchase stocks, say, and we're interested in the S&P 500. So we want to, and we're only interested in those. So S&P 500 is 500 companies. Okay, then we can look at the stock price of each one of them and say, here's the first company, their value is going to be in the first coordinate. Here's the second company, their value is in the second coordinate, all the way to 500. So we're talking about R500. Okay, a 500-dimensional vector space. Okay, now there is no notion whatsoever of geometry there. Okay, it doesn't make any sense. You could say, well, here's the vector of the S&P 500 today, and here's the vector of the S&P 500 tomorrow. It doesn't make any sense to measure the angle between these two vectors. They're vectors, but there's no notion of angle between them. Okay, good. So rant over. Okay, so the definition of the length of a vector. The length of a vector in this textbook, I usually prefer to write it with 2 bars, but in this textbook, that is to say with double bars on each side, bar, and then on the other side, another 2 bars. But in this textbook, they use single bars, just like absolute value, so we'll follow the author's lead. The definition is the square root of the dot product. This is nice in that it's true for every single dimension. Okay, it's true in dimension 1. It's true in dimension 2370. Good. Any question about this? This is fine? Good. So, where did we go? Good. So now we want to talk about, remark about adding vectors. So generally speaking, when we're talking about vectors like this, remember the dichotomy of interpretation. You can interpret them as positions, or you can interpret them as increments. So in the current remark, we're construing them as being increments. So suppose that we have 2 vectors, so given x and y in Rn. So now, we're going to consider them to be arrows. And to give you something concrete to think about, you can imagine that the tail, that is to say not the pointy side but the other side of the arrow, is at the origin, and they're each pointing at their coordinates. Okay, now furthermore, you have the origin and you've got the two places that the vectors are pointing to, right, in an n-dimensional space. This is conceivably in 2,370 dimensions. So you've got 3 points: the origin, the position that x is pointing to, and you've got the position that y is pointing to. Okay, now I want you to, through the origin and where x is pointing, I want you to fit a plane and notice that it would spin. It would spin around, wouldn't it? Okay, now spin it around until it hits the position that y is pointing to. Because that's 3 points, so that plane would go around and hit it. So now what I'm saying is that we're grabbing that plane, and I'm going to draw right here on the page. Okay, so I'm going to make a two-dimensional drawing, but I'm not sacrificing anything. Okay. So suppose that this is x. And this y. And what I insist is that it makes perfectly good sense for me to make a two-dimensional drawing for this case. Okay, so now every school child knows, how do you add two vectors visually? Tip to tail, right? So then, in particular, these are vectors. These are increments. So if I were to take x and move it around, it'd still be x. It's still x, moving it around. So what I'm going to do is I'm going to take y and make another copy of it and put it over here. So this is still y. It's just another copy of y, and I put it over there. So then what is x plus y? Well, it starts here at the tail of x, and then ends here at the head of y. So it would be like this. So this is x plus y. It's x plus y and not y plus x because we did x first and then we did y. So it's first x, then y. But if it's good for y, if I can move y around, then it's good for x too, right? I could move x around and put an x right here. And then what if we do y first and then x? Then the sum would be y plus x, right? It would be y plus x. Well, this is a visual representation of why the addition of vectors must commute. Okay, so this parallelogram, this shape of parallelogram, the sum of vectors is this diagonal of that parallelogram. What's the other diagonal? The difference, right? The subtraction. Let's look at it for a moment. So if this is x, and this is y. I'm trying to draw another exact copy of that over there, but anyway. So the other diagonal, that is to say, not this one that happens to be longer, but this one that happens to be shorter. Okay, now I'm going to draw one of them. How about this one? The other one, by the other one I mean I could take that blue arrow and turn it around. So my question to you is, this blue one that I've drawn, is it, which subtraction is it? Is it x minus y or is it y minus x? Well, let's think about it. The orientation of this blue vector is from tail to head, right? It's from tail to head. And the question you have to ask is that if instead of traversing the blue, if instead of doing the blue, we were to do the green component and then the red component, we'd have to do the green component and then the red component, right? Starting from the tail, First the green part, then the red part. So when you're traveling the green part, are you traveling in the same sense that y is pointing? No, you're traveling in the opposite sense. Y is pointing that way. So if you start on the blue and on blue's tail and travel along green, you're traveling in the negative y direction. Negative y. And then when you travel the red part, are you traveling in the same sense as x or the opposite sense? Same sense. So opposite of y, same as x. So what is this one? This is negative y plus x, or, if you like, x minus y. Okay, similarly, let's try it the other way, because my teacher sense, I'm looking out and trying to feel the crowd, and y'all don't feel very confident on this one to me. Okay, so now the blue vector is going that way. So what I want you to do is I want you to travel along the red and green path. And I want you to ask yourself, in each case, when you're traveling on the red, am I traveling in the same sense as red or the opposite sense? And then when you're traveling with the green, is it the same sense or the opposite sense? Opposite of x, right? Because when you're traveling in the red component, you've got to go this way, so it's opposite of x, and then with the green, same as y. So what is this one? Y minus x. Very good. Any question about these? So as a result, it's a little bit crowded here. So I'll just draw it. Try to draw it. The sum and difference of parallelograms, the sum and difference of vectors is very succinctly given by the diagonals of parallelograms. That is to say, this blue one is the sum, and this graphite one is one of the differences. Is it red minus green, or is it green minus red, the one I just drew? Red minus green, because you're traveling in the opposite sense of green and in the same sense as red. Good. Any question about this? So go home and practice this, because fairly soon, before the semester is over anyway, we're going to be talking about these vectors are objects with a one-dimensional oriented object. They're like little line segments that have an orientation. This you're going with it, this you're going against it. By the end of the semester, we're going to be talking about two-dimensional oriented objects and three-dimensional oriented objects, and I'm going to be asking you, for this two-dimensional oriented object, are you traveling, whatever that's going to mean? Are you using it in the same sense as its current orientation or the opposite sense? Okay, so get used to it with one dimensions, because n dimensions is coming. Good. So now, the definition of angle. So again, we say let x and y be in the reals, are in Rn. Then I can again draw them to a two-dimensional representation of this n-dimensional situation, x and y. Now remember, these are free vectors, and I'm putting their tails together. Free vectors meaning, by that I mean increments. I'm putting their tails together because that's going to be the easiest way for us to talk about them. But remember, you can move them around. So what we want to have is we want to have this angle right here. And we want to have the same notion of angle that you learned from trigonometry. We want it to be the same as before. So here's how we're going to do it. So here's x and y. We're going to compute the difference of x and y. So how about this one? So which one did I just draw? That's y minus x, because it's opposite of x, same as y. And that looks like a right angle, but it's not. Okay, that's just I wish I hadn't drawn it that way. Okay, is all that is. Okay, so this is a triangle. It's a triangle, and it has side lengths, magnitude of x, magnitude of y, the length thingy, and length of this one. Okay, now, if it were exactly a right angle, if this one were the right angle, if theta were a right angle, then how would the side lengths be related to each other? By the Pythagorean theorem, right? If theta was a right angle, then that would be the hypotenuse. That would be the hypotenuse, and the result would be that the length of x squared plus the length of y squared is the hypotenuse squared. Of course, that's only good when theta is a right angle. Now, if theta is not a right angle, in trigonometry you learned how you can deal with it even better, how you can continue this to make a slight correction to Pythagoras and get the general result. So what's the name for the correction to Pythagoras? The law of cosines, right? So generally, yes. Generally, it will be that the hypotenuse squared is the side lengths, the sum of the side lengths squared, minus twice times the product of the lengths, and then importantly, what? The cosine of the angle in between them. So what this is going to do is this is going to tell us how much time do we have? We're basically out of time. So what this is going to do is it will tell us how to solve for that angle. It will tell us how to solve for that angle, and it will be a consequence of the dot product. Now, last thing, why will it be a consequence of the dot product? No, the dot product is not defined that way.
X dot y cosine theorem?
No, that's a consequence of the definition.
Oh,
It's
okay.
other way around.
Okay.
Why is this going to be a consequence of the dot product? Because that's defined in terms of the dot product.
Okay.
All of these vertical bars are defined in terms of the dot product. Yes? Yes. Thank you. Okay, have a nice Thursday. Problem section tomorrow.